Welcome again, everybody. This is the second part of the two talks that Francois Gelis is offering us on thermalization in the Gelis equation. You see on the slide the three topics that we covered last time around, and I'm really looking forward to how this is now going to come together for a calculation that is actually attacking QCD. So, Francois, please take it away.
Thank you. Yes, so indeed, this is the outline. In blue are the topics I covered 2 weeks ago. So that was a brief overview of the relevant aspects of heavy ion collisions, some general ideas about thermalization, and then how we think we can describe the initial state of these collisions with an effective theory inspired from QCD, which is a color glass condensate. And today I want to go to the heart of what we're doing now. I will first start with old stuff, which is to give you a feeling of what has been tried already, and then the main part of today will be how we can use a 2PI effective action formalism to attack this problem. So before I start with the semi-classical treatment, I want to go back to a formula I flashed last time, which is this one at the top here. It's a totally general and exact formula. It's in any quantum field theory, in fact. You can relate the leading order of some observable, some inclusive observable, it has to be an inclusive observable, to the next to leading order one, so 3 level and 1 loop, by acting on the 3 level calculation with a certain operator, which is quadratic in derivatives respect to the initial condition for the classical field. So this T is like the generator of the shifts of this initial field. If you act on some quantity with the exponential of this operator, it's just shifting the initial value of this field in the quantity you apply this operator to. So now this can be used to construct generalizations that goes beyond one loop. So the first line is just a recap of what I just said. So if you sum leading order plus 1 loop, it's 1 plus this operator acting on the leading order. This is exact. But I told you that the next to leading order, if you take it by itself, it's a bit pathological because it contains some terms that have that grow with time due to instabilities, for instance. So it's if you truncate right after the 1 loop, you're not getting anything very useful for as far as physics is concerned. But you could try to be a bit bolder and do a resummation by noticing that this operator here looks like the beginning of the Taylor expansion of an exponential. So with the dots here, what can be done is to promote this the beginning of this series into an exponential. And in fact, there is a justification behind that, which is that this exponentiation amounts to resumming at every order of the perturbative expansion the terms that have the fastest growth with time. This gives you this exponential. And now the trick is to note that if you have an exponential of something which is quadratic in derivatives, it's really like convoluting your quantity with a Gaussian. With this G of alpha is a Gaussian distribution, so you need only to specify what's a 2-point function, and it's precisely the gamma mu nu that was in this operator inside the exponential. So it's something which is very easy to implement numerically because You just take the code for solving the problem at leading order. So it's essentially a code that solves the classical equations of motion starting from some initial condition. But now, on top of that, you add a Gaussian average over fluctuations of the initial condition. So this is called the classical statistical approximation. By design, the time evolution is still classical, but the initial conditions fluctuate with this Gaussian and over this Gaussian ensemble. And by design, if you tune properly the two-point function of the Gaussian, you recover exactly the one loop result, plus a bunch of other things on top of that. But it's only, of course, you don't get the full all orders result. You get only a subset from the two loop result, a subset from the three loop results, and so on. Another thing I want to mention is that the Fourier transform gamma k of this kernel, gamma mu nu, is, you could think of it as a momentum distribution of the initial fluctuation. So it's telling you what are the momenta in the initial present in the initial conditions. And then this has been implemented by various groups using various choices for this gamma. One choice is to just take at face value the one loop calculation, which describes totally this gamma. And then you will realize that the Fourier transform gamma of k is 1/2 plus a function which is steeply falling with k. You could think of this fk as an occupation number for the Fourier modes, and it has a compact support. But the problem is a 1/2 because this one is flat and extends all the way to infinite momentum. And in this approximation, it causes UV divergences, and furthermore, because it's an approximation of the full theory, but it's not the full theory, this approximation is not renormalizable. So it means that when you implement it on a lattice, there is no continuum limit, and you may get reasonable results if your lattice spacing is not too small, and if you try to make the lattice spacing super small, then you get nonsense, essentially. Another choice which has been made is to just drop the 1/2. So now the gamma k has a compact support. This makes this approximation UV finite, but it drops some important pieces which are essential for isotropization. So this is a state of this classical statistical approximation applied to heavy ion collisions. It's not very satisfactory because you can have either something which is UV finite but misses some physically important contributions, or something which has these contributions but is not renormalizable. Let me switch now to kinetic theory. So kinetic theory is just a Boltzmann equation. So here I wrote a kind of cartoon Boltzmann equation for two-body scattering. F is the occupation number. 1, 2, 3, 4 are labeling the two particles in the initial state and in the final state. You have the energy momentum conservation delta function and squared transition probability, if you want, and then a certain combination of the occupation numbers that has both cubic and quartic terms. And here it's a bit easier to see the problem if you drop the quartic term. So in fact, if you follow the derivation of the Boltzmann equation from the underlying quantum field theory, you will see that if you drop the 1/2 I was talking about in the previous slide, you're not going to get the quadratic terms in the Boltzmann equation. So now this is, you may think that this is fine if f is large, because then the cubic terms will dominate over the quadratic terms, but, and there is a big caveat here, this is true only if all the momenta are within the support of this function. Okay, so now if you have a system which is longitudinally expanding, the PZ, the Z component of the momentum shrinks, and this distribution F is very anisotropic. You could think of it as a pancake in momentum space, with a support only almost at PZ equals 0. And therefore, if you try to look at a scattering that will produce particles 3 and 4 off this plane, then the cubic terms always have one momentum which is evaluated in the region where F is small. So in fact, for the processes that isotropize the system, the cubic terms are not the leading ones, even though they are very large inside the support of F. And the quadratic terms, even though they are on the paper subdominant, they are very important for isotropization because they are the only ones that can produce isotropization. So this was seen by Kurkela and Zhu in 2015, I think. The paper comes from, the plot comes from their paper. And here they compare, when you follow these lines, it's like following the time evolution of the system. On the vertical axis, you have the anisotropy measured by the ratio of the transverse to longitudinal pressure. And on the horizontal axis, you have a number that characterizes how large is the occupation number. And let's look only at the solid lines. The initial condition is here, and lambdas are various couplings. And the black curve corresponds to the semi-classical approximation, so where you drop the quadratic terms in the Boltzmann equation, and you see that it's only accurate at the very beginning, at very early times, and very quickly it takes a totally different behavior compared to what you get with the full Boltzmann equation. And you see that with the full Boltzmann equation, you do get isotropization because the end of the evolution is always on the horizontal line where the anisotropy is 0. So Pt is the same as Pl. And what they did also in this paper is to show that their kinetic Boltzmann equation has a smooth matching with hydrodynamics, which is satisfactory. So the red dashed curves are some hydrodynamical calculation, and the black solid line is the kinetic theory. But there are a few caveats to a kinetic approach, which is that there are a certain number of assumptions in the derivation of the Boltzmann equation which are not necessarily true. So in particular, you need to have long-lived quasi-particles, you need moderate occupation numbers and small spatial gradients. And all of these hypotheses have problems at early times in heavy ion collisions because the occupation number is initially large, as the inverse coupling. The expansion rate is 1 over the time, which is large also at the beginning. And presumably at the beginning, if you were computing the self-energy of the gluons, you will find a significant imaginary part, which means that they have a short lifetime and you don't really have well-defined quasi-particles yet. So what we need is a framework that could handle large occupation numbers, large gradients, and where we don't really need the hypothesis of having quasi-particles, but we can deal directly with quantum fields. So this framework exists. It's the 2pi effective action. So let me first recall you at least a sketch of how you get the Boltzmann equation from the underlying quantum field theory. So starting from the full quantum field theory, you write equations which are known as the Dyson-Schwinger equation. So they tell you how the full propagator G is related to the free propagator G0 if you know the self-energy sigma. Of course, this equation by itself is exact, but is not super useful because sigma is an infinite series of terms in terms of the propagator. So it becomes useful when you truncate what you put in the self-energy. And so if you do a truncation of sigma at two loops, and then you assume that the spatial gradients are small, and you do a quasi-particle approximation, so it means, roughly speaking, the propagator is proportional to an occupation number times a delta function forcing the momentum to be on shell, then you get the Boltzmann equation without any further approximation. So a legitimate question will be to try and solve directly the Dyson-Schwinger equation. So you will solve a certain approximation of the underlying quantum field theory, but without all these assumptions that are added to get the Boltzmann equation. So the formalism exists for doing this. I recall you here that the usual quantum effective action gamma of phi is a generalization of the classical action that will include all quantum corrections under the assumption that you know the field expectation value phi. So this is the 1 pi, if you want, one particle irreducible effective action, because if you think of its representation in terms of graphs, it has only one particle irreducible graph, so graphs which are still connected if you cut one line, one propagator through them. And the 2 pi effective action is a generalization of this concept. It depends on a field and on a propagator. And it's the generalization of the classical action if you pretend that you know the expectation value of the field and the exact propagator G. And the reason why, if you knew this object, it's more powerful than knowing just gamma of phi comes from the fact that when you say you know the propagator, it means you've already packed a lot of the complexity of the problem in what you call G, in the propagator. So the 2 pi quantum effective action for a scalar field theory takes this form. It's a sum of several terms. You have the classical action, S of phi. You have a one loop term, which is just a trace of the logarithm of the propagator. You have another term which involves this G0 inverse. I will tell you in a second what this is. And then you have phi, which is a sum of all vacuum graphs which are two particle irreducible and built with phi and the exact propagator G. So two particle irreducible means that if you take any graphs in this phi and you cut two lines, it's still connected. So there are fewer graphs in this phi than in the one particle irreducible effective action. G0 inverse, or G0, is a propagator in the background field phi, but with no further or no additional correction except for the background field phi. So its inverse is just D'Alembertian plus m squared plus g squared over 2 phi squared. This is for a scalar theory with a phi-4 interaction. And G, as I said, is the exact propagator. And if you happen to know this functional, gamma, then you can determine phi and G by solving equations of motion which are very similar to what you do in classical mechanics, where you find the extremum of the action with respect to coordinates. But except that here what you call the coordinates are the field on the one hand and the propagator. You have these two objects that act as coordinates for this action. So if you make that a little more explicit, since the first three terms are rather explicit, you can directly compute these derivatives, and then you will have an extra term with the derivatives of this functional phi. So the equations of motion look like this. This is the one where you say gamma is extremum with respect to variations of phi, and the one that says that gamma is extremum with respect to the variations of G is the second equation. And you see that you get these terms with the derivative of the functional phi with respect to the field or with respect to the propagator. So these equations are still exact, but not very useful yet. To make them useful, you need to do a certain truncation of the 2pi functional phi, and the approximation we made here is to truncate this functional at the order G4. So this includes these three graphs. The lines here are the exact propagator G, and the red dots are the field phi. Okay, so you have two graphs independent of the field and one that depends on the field. So if you choose this truncation, then it becomes totally explicit, because now you can compute these derivatives explicitly in the two equations, and you have equations, coupled equations for phi and G. It's a bit inconvenient to write them in this form because G is a complex valued propagator in general. So it's more convenient to do a little bit of massaging of these equations. One thing to recall is that here, if it's not written very explicitly, all the times in these equations, they live on the Schwinger-Keldysh contour that has two branches. So it starts at minus infinity, goes to plus infinity, and goes back to minus infinity. So you should view these propagators as, for instance, the propagator can have four possibilities depending on whether x0 and y0 live on the plus or minus branch of this contour. So this is what is denoted with the subscripts minus, plus, etc. So a convenient choice is to choose f as the sum or the half sum of g minus plus and g plus minus, and rho as minus I times their difference. These two propagators, g minus plus and g plus minus, it's easy to see that they are complex conjugate of each other. So f and rho are both real valued with this choice, with the I in particular in rho. And you can rewrite everything in terms of f and rho. So these are the form of the equations you get in terms of f and rho. You get an equation for the field, an equation for f, and one for rho. They all have this T of x, which is the tadpole. It's just the propagator f at equal points times g squared over 2. So it's really just the tadpole which is correcting the mass. And then you have in the right hand side terms which contain self-energies. I will show you on the next slide what these self-energies are. And they have integrals over time from the initial time to x0 or from y0 to x0. So this is a specificity of these equations. It's that they have these memory integrals, and therefore they remember, at least to some extent, all the past history of the system. Of course, they are causal. They don't depend on times larger than x0 if you're looking at the evolution in x0. But they can depend on all the past history of the system. And at the order where we truncated the phi functional, we have these explicit formulas for the self-energies that appear in this equation. So here it's written in coordinate space. And one thing I want to mention is that out of these self-energies, sigma f is UV finite, and sigma rho and pi rho contain UV divergences. So now let me tell you a bit more about renormalization, because these self-energies are UV divergent. The tadpole here is also UV divergent, so something must be done about this. So as usual, the tadpole, it's in four space-time dimensions, so the tadpole has a quadratic UV divergence, which is of order g squared. But because the tadpole is momentum independent, it contributes only to the mass counterterm. It doesn't contribute to the field renormalization. But hidden in the tadpole, some graphs contain one-loop corrections to the vertex, which have logarithmic UV divergence. I will show you why on the next slide. And then you have also the two-loop self-energies. So the self-energies here have are two-loop corrections. And these also will contribute to the mass and field renormalization, but at a lower order, which is G4. Now comes the complication, because what we're doing when we solve these equations of motion is we are doing a certain kind of resummation. The counter terms depend on G square to all orders. The fixed order counter terms that we know, that we are familiar with from perturbation theory, they are not sufficient to remove all UV divergences. So let me illustrate that in the case of the tadpole. So what I show here in red is a full propagator F that you will get by solving the equation of motion. And what I draw on the right-hand side is what this contains in terms of the Baire propagator, say F0 or G0. So it's in fact an infinite series of the graphs that are sometimes known as the super daisy graphs. So I've shown only a few of the beginning of this expansion. And you see that you have regular tadpoles, like here, or this loop here, or that loop, these loops here. But then you have this loop here, which is like a vertex correction. It's a one loop correction to a 4-point function. And here it's iterated. You have two of them. So it means that even so we're talking only about something that looks like a tadpole, to make it fully finite, we need both a counter term for the mass and a counter term for the coupling. They can be determined fairly easily in this case. So first of all, we have to think about this problem in the vacuum. And we will calculate the counter terms in the vacuum, and then we need to show that when we include matter, when we include, say, distribution of particles, for instance, these counter terms calculated in the vacuum are sufficient to make everything finite. So in a sense, you don't need the counter terms to know about the particle distribution. So the first thing to do is to write a gap equation for the renormalized mass. So you write that the renormalized mass is equal to, it's just writing this equation in a slightly more detail, in fact. So it's the renormalized mass is the renormalized mass plus the counter term plus the vertex accompanied the coupling, the renormalized coupling with the associated counter term times the 1/2, which is a symmetry factor, times the integral of the vacuum F over all momenta. And then you can solve this trivially by finding the counter term for the mass in terms of the renormalized mass and the Baire coupling. So of course, the renormalized mass, you can choose it in principle as you wish. It's not something that will come out of this equation. So given a renormalized mass that you choose, you find a certain counter term. And then you have a second equation, which is also a recursive equation for finding the coupling. So it's telling you that the coupling is equal to the Baire coupling, so the renormalized plus counter term coupling, times, plus the Baire coupling times the renormalized coupling, and now you have an integral with two propagators. So it's the two propagators are the two propagators of this loop here. It turns out that if you work out the loop, one is a f and the other one is a rho. I've eliminated all the i's and all the factors, and it gives a minus sign. So this you can solve for the bare coupling. You will find that the bare coupling, so the sum of the renormalized plus counter term, is given by this formula. And you see that now the coupling is in the denominator. So if you were expanding this, you will find indeed that this counter term contains all orders in the coupling. And now that you've found the counter terms, now you know everything, you know delta m square and delta g square. You can ask the question about whether they are sufficient to make everything finite when you include matter. So now you have a new gap equation. Big capital M is the mass in the presence of a particle distribution, for instance. So it includes the thermal mass that will be produced by the distribution of particles. So it's the same equation as before, but with mr square here and in the propagator replaced by the full mass. And you similarly have a coupling which is modified by the presence of matter. So now I call it capital G square, but it's given by the same style of equation, except that in the propagators now you have the full mass. So you can solve this for big G square, and you will find this using the previously determined counter term. And you see that now everything is fine because you have these momentum integrals, but you have a difference of two such integrals. They are both logarithmically divergent, but the difference is finite. So in fact, the dressed coupling in the presence of matter is finite if you've determined the counter term in the vacuum. And the same works for the mass. It's a little bit more complicated to see, but it works pretty much in the same way. The conclusion is that the big M square, so the mass that solves the gap equation in the presence of matter, is also UV finite with the mass counter term and coupling counter term determined in vacuum. So what I discussed here is the simplest, which is the renormalization of the two PI equations when you include only the tadpole. It's known that it's possible to do it beyond the tadpole approximation, but now it requires also a counter term delta z for the field renormalization. It's a lot more complicated to implement in practice, and we've not implemented that in this work. So we stopped the renormalization at what I told you earlier, which is remove totally the UV divergences coming from the tadpole. But we have estimates for what's missing. So, of course, the mass counter term is the largest subtraction of all because it comes from a quadratic divergence. The delta G square that I've described in the previous slides provides a 10 to 15% correction on top of that, with G4 equal 500, which is a kind of moderate coupling for this type of problem. And then we've also estimated the field renormalization counter term, delta Z, and we found that it will bring an additional 1% correction. So that's the reason why we're not including it. But if one wanted to try larger couplings, it will become more important, of course, because it grows like G4. So now let me tell you a few words about the numerical implementation. So in fact, when we started this project, we saw that the main obstacle will be the computational power we have access to. But it turns out that the bigger concern is the memory you need, in fact, because of the necessity to store the past values of the propagators. So let me give you a feeling for this problem. Suppose we discretize three-dimensional space on a grid that has n cubed points, so n points in every spatial direction. So with fixed times x0 and y0, a propagator will use n to the 6 numbers, because you have the position for x and the position for y. Now, of course, we're not going to store all the full history of the system, but let's say we store the last n sub t time steps. So now the memory you need will be n6 times 1/2 of nt squared, 1/2 because the propagators have a symmetry, so you need to store them only when y0 is smaller than x0. And now let's take some numbers. You take nt equal 1000, n equal 500, simple precision to save some space. You end up with almost 30 times 10 to the 9 terabytes, which of course we don't have. So what this means is that the memory needs are large, and we must, it's not that we can, we must assume that the system has some spatial symmetries to reduce the memory that we need. So let me tell you what we assumed. So first of all, because we want to discuss collision at high energy, a collision at high energy is approximately invariant under the boosts along the collision axis, so the z direction here. And the best way to make this boost invariance manifest is to use the so-called Milne coordinates. So you map the forward light cone of the collision. So the horizontal axis is the axis of the collision. The vertical axis is time. These are the light cones. And everything in the upper light cone is after the collision. So we map this region of space-time with the proper time, which is defined as square root of the ordinary time squared minus z squared, and the rapidity, which is 1/2 of the logarithm of t plus z divided by t minus z. And then the boost invariance is just translation invariance in this rapidity variable at fixed time. So it's very easy, it's just another form of translation invariance. So now the symmetries we assume is that we have translation and rotation invariance in the transverse plane, so the plane transverse to the collision axis. So it means that all propagators depend only on the distance separating their transverse coordinates. And the fact that we have boost invariance in the z direction means that they depend on the rapidities only through the absolute value of the rapidity difference. And now, so we discretize the transverse radius with n transverse points. We discretize the rapidity difference with n eta points. And now the memory we need is just 1/2 of nt squared. This is always there, times n perp times n eta. And then if we take these numbers still in single precision, we get to 1/2 terabyte, which is large, but doable. And if we lower a little bit these numbers, we can bring it to a couple hundred gigabytes. So now this is not totally free. The fact that we use the Milne coordinates, so proper time and rapidity, brings a few complications. One of them is that if you discretize in this coordinate, so it means you're going to consider a fixed volume in x transverse and eta, it corresponds to a time-dependent volume in the z coordinate. Because at a fixed value of eta corresponds to a z which increases with time. So this means that in particular, the lattice spacing, when expressed in physical units, in say meters, in the z direction, it will be stretched with time, and then there will be a point, a time beyond which you will not have the sufficient resolution in z to describe the physical scales of the problem. The second complication is that the UV cutoff in PZ is time dependent, so it means that the UV counterterms will be time dependent. So you have to solve the equations I've shown you earlier for finding the counterterms. You have to solve them at every time step of your algorithm. You cannot calculate once and for all the counterterms. Second complication, it's that the analog of plane waves, so the free field solutions, if you wish, are not exponentials of momentum dot the position. They are Hankel functions. So there are some kind of Bessel functions they depend on the transverse mass. This is square root of P transverse squared plus the square of the mass. And they depend on this nu, which is the Fourier conjugate to eta, to the spatial rapidity. If you want to get some intuition over nu, it's roughly pz times the time, it's dimensionless. But the main difficulty is that in some of the stages of the algorithm, you need the free propagators, and the free propagators, they have a simple expression in terms of the Hankel function, so you need to write some code to compute these Hankel functions. And the third complication is that to compute the self-energies, so if you compute the self-energies in momentum space, they are given by convolutions in momentum space, which are a bit complicated to evaluate. And in fact, the standard strategy to calculate convolutions is to go to coordinate space where they become ordinary products. And then you Fourier transform back to momentum space. The problem is that if you know a function only as a function of the radius, as the difference of the transverse coordinates, then the Fourier transform to go to the transverse momentum is not really, well, it's a Fourier transform, but it's only a one-dimensional integral if you have this kernel, which is a Bessel function. So in fact, it's known as a Hankel transform. So it means that the usual algorithms for doing numerically Fourier transforms, such as FFT, fast Fourier transforms, they are not applicable to this case because they work only when you have a sine or a cosine here, not a Bessel function. So we had also to look in the literature to find if this was known. So let me first flash the formulas for the Baire propagators to explain why we need the Hankel function. So the F0 and ρ0 propagators, they are given by these formulas in terms of Hankel functions. And they are needed here, you see, when you compute the counter terms, you have integrals over momentums, and in the integrand you have these vacuum propagators. So we had to write some piece of code for calculating Hankel functions. And now for the Fourier transform, for the Hankel transforms, after some searching, we found that this was a known problem in the field of optics. In fact, we found some papers from, not so old papers, from 20, 25 years ago, where people working on optics had designed algorithms for calculating Hankel transforms. So the one we used is known as quasi-discrete Hankel transform. And it works as follows. You have to choose, you have to find the zeros of the Bessel function J0, you denote them alpha I. You choose some length R and momentum P. This will be basically the support of the functions you consider in R and in P. And the discrete radii are defined as alpha I over P, and the discrete momenta are defined as alpha K over R. And then the formulas for doing the Hankel transform and its inverse are given here. So they are very simple formulas. These weights that depend on Bessel functions, they are a little annoying, but you need only to calculate them once. You calculate them, you store them in an array, and you're done. They are not time dependent. I should tell you a little more about the quasi in the name of this algorithm. It's because there is a little cheat when I write these formulas. So in fact, strictly speaking, one of the two formulas is slightly incorrect. So if you define f in terms of f tilde by the first formula, then the second formula is not exact. It's an approximation of the inverse. It's only exact if n goes to infinity. But at finite n, there is a little violation of the second formula. But what we realized by looking at this literature from optics is that if you choose a product R times P, so these two, this length and this momentum here, such that it's near the n plus 1 zero of J0, so the first zero you don't use in the formulas, then you can make the error very small. So in fact, for n equal 500, the error, or relative error, is of the order of 10 to the minus 14. So since we're working in simple precision, it's definitely good enough. And how is a time step done? So what is shown on this grid is tau and tau prime, so the two time arguments of a propagator. We only consider tau prime less than tau because the propagators are either symmetric or anti-symmetric. So each dot corresponds to one pair tau tau prime. And suppose we know all the propagators corresponding to the black dots. So the next time step, we want to find all the propagators on the next column. And this is done in two stages. First, we do one step in tau at fixed tau prime. So this gives you all the green dots. And you need some special treatment to find the red dot, because this one requires to do a time step on both times simultaneously. So it's a slightly different, it's the same algorithm, but its implementation is a little different. So let me turn to some results. To set up the computation, you need to specify a few things. You need to choose an initial time, an initial occupation number, and as part of the choice of the initial occupation number, you have typically one momentum scale, which I will call Q here, which tells you how far goes the support of the particles in momentum space initially. You need to choose the initial value of the field and its time derivative, but for simplicity, in this first approach, we've just taken null fields here, so we have only the propagators. You need to choose the renormalized mass and the renormalized coupling. We had G square around 22. It may sound large, but it's not a super large coupling. So to give you a feeling of how strong this coupling is, you can evaluate the ratio of viscosity to entropy at this coupling, and it's around 25 for the 5-4 theory. So it's significantly above 1, and it's still in the regime of rather intermediate couplings, let's say. Not super weak, but not large couplings either. I want to mention just one thing in passing. It's the fact that the 5-4 theory, scalar 5-4 theory in 4 dimensions, is suspected to be trivial. So what this means is that in fact, if it is really trivial, it means that the continuum limit exists only at null coupling. So it's a theory where you cannot really put consistently interactions. So here, because we're working with UV cutoff, we're not affected by this problem. But what this means is that if we try to take a very large UV cutoff, we will be forced to take a smaller renormalized coupling because of this, or said differently, at a fixed UV cutoff, there is a maximal renormalized coupling you can choose before everything breaks down. I don't think we have reached it yet here, but it's probably not possible to increase much further the coupling compared to the values we have here. One thing I should mention is how we get some physically interesting properties of the system out of the propagators, because when you solve the equations, all you get are the propagators. So the first thing you can extract is the occupation number. So the assumption here is that you try to do a quasi-particle decomposition of your propagator. It's all contained in the propagator f, and in fact the combination you have to consider is f times its time derivative minus the square of the first derivative. You take the square root of that and you multiply by time, and it's 1/2 plus the occupation number. This you can see fairly easily starting from this formula here, for instance. All you need to know is the Wronskian of the Hankel functions, which is simple. And the beauty of this formula is that it gives you the occupation number even if you don't know the mass of the particles. This is particularly useful because because you have a high density of matter in this problem. Most likely the masses of the particles will be dressed by thermal corrections, and you don't know what they are at this point. So having a way to extract the occupation numbers that doesn't rely on knowing the mass is handy. We can also extract the thermal mass. For this, it's convenient to consider this particular combination of F and rho. And if also you assume a quasi-particle ansatz, this combination turns out to be just a product of Hankel functions. And then we look at the oscillation period of, say, the second factor, so the tau prime dependence. It's not exactly periodic, but if you view it it's a complex number that revolves around the origin in the complex plane. So you can define a kind of pseudo period, which is the time it takes to do one rotation around the origin in the complex plane. And then if you also know the period of oscillations of the Hankel function, and you compare the two, you can find what was the transverse mass here. So using this, we can extract the thermal mass. So now let me show you some results. The first series of plots is showing. It's just to convince you that the residual UV dependence is not too large. So here it was an even simpler form of renormalization than what I described, because we subtracted the tadpole to remove the quadratic divergence, but we didn't renormalize the coupling. And you see, so the three curves, the blue, orange, and green, correspond to varying the cutoffs either in nu or in p transverse. And you see that the variation is around 15% roughly, 15 to 20%. But now, the rest of the results I will show you have also the renormalization of the coupling. So now what we have here is the extracted occupation number as a function of momentum at various times. And the first column is showing that for free streaming. So free streaming is the approximation where you just discard the memory integrals. You just have the tadpole, but you don't have the memory integrals, which are believed to bring collisions among the particles. And the column on the right is showing this for the full calculation with the memory integrals. So let's start by, say, the column on the left. At early times, in orange you have the distribution in PZ, and in blue you have the distribution in P-perp. At early times, Q tau of order 1, the transverse and longitudinal distributions are roughly the same. It's by design, it's because we've tuned the initial conditions so that it's like that. But then, as you increase the time, you see that the distribution in P-perp almost doesn't change, and the distribution in PZ is shrinking towards the origin. And this is very well understood. It's just free streaming, which reduces the support of the occupation number like 1 over tau. Now you can compare this with the full calculation that has the memory integrals at the same times with the same initial conditions. So now you see that there is a little shrinking of the PZ distribution compared to the P-perp distribution, but the difference between the two is much less pronounced, and it's rather small, in fact. So we interpret this as a sign of the fact that the collisions included via the memory integrals are competing against the expansion, and they try to make the system less anisotropic or more isotropic, depending on how you want to see it. So now what I'm showing on this series of 3 plots is the extracted thermal mass. So here capital M is the extracted mass from which we subtract the bare renormalized mass. So it's a thermal contribution to the mass as a function of momentum. So the orange curve shows the PZ dependence and the blue curve shows the P-perp dependence at various times. So here I should maybe go back here. You see that when you carry out this extraction, you have to do it, you have to choose the new and P-perp at which you do it. And there is no guarantee that the mass you extract is the same at all momenta. And in fact, if your calculation is including a self-energy which is momentum dependent, what you extract from this should be momentum dependent. So in fact, we do this extraction at all news and PTs, and then we plot the extracted mass as a function of longitudinal and transverse momentum. So this is what is done here. So you see that at a time which is rather short compared to the initial time, not long after the initial time, you have a very different thermal mass in the PT and PZ direction. So you have, the self-energy which is recent on the propagator has a rather strong anisotropy. And then as you increase the time, so you evolve with the collisions, with the memory integrals, then progressively the transverse dependence and longitudinal dependence of this mass become more and more similar. And at the last time we have here, they are almost identical. So this is another sign of isotropization going on in the system, but here it's not the isotropization of the momenta of the particles, it's a more microscopic quantity which we are looking here, which is the isotropization of the self-energy or the effective mass of the particles. Another thing we extracted, this is done just by integrating over all momenta the occupation number, is the number density, and n bar here is the proper time times the number density. So if the system was expanding longitudinally and you have only number conserving collisions, then this n bar should be constant. And in fact, this is what we see when or approximately we see it, when we include only the tadpole. You see it's the orange curve, and it's almost constant from the very beginning. And the blue curve is showing the same quantity, but now with a full calculation that has also the memory integrals. And in this case, there is a significant drop of this density at the beginning, and then it stabilizes. And we interpret this drop as the fact that there are some number changing processes which are active during this period of time. And it decreases because our initial condition had too many particles compared to what it should have had if the system was in equilibrium. So then the trend is to decrease, to make the number of particles decrease. Okay, so I'm reaching the end of my talk, and I just have one slide of summary to wrap it up. So what we've done is to study the 2pi equations of motion truncated at order G4 in the Milne coordinates, which are the most appropriate to describe a collision at high energy. This, of course, is not for Young-Mills, it's for a toy model, which is a scalar field theory. We had to assume some symmetry, some spatial symmetries to make it manageable, mostly to reduce the amount of memory we need. And as it turns out, for this kind of numerical problem, the memory, so the amount of memory you have and how fast it is as important as the pure computational power to crunch the numbers. It's just what takes, in fact, a significant amount of time in carrying out this algorithm is just the time it takes to read and write of the order of 1 terabyte of memory at each time step. So we see a rather distinct trend towards isotropization. And the extracted thermal mass also shows isotropization. We see variation of the number density, which is not the same as in kinetic theory. So it means that we have the physics we include, even so the graphs included in the self-energies are the same. Since we don't do the quasi-particle approximation, we can have off-shell, how to say, the momenta can be off-shell, and this allows number-changing processes, which we do see. So we're thinking of some extensions. I would say among the three listed, the first two are realistic in a rather short time frame, and the last one is probably not feasible with the resources we have now. So first extension, of course, is to improve the renormalization to fully remove all UV, all dependence on the UV cutoffs from the two-loop self-energies. Another interesting thing we can study is to let the field be non-zero in order to study how a classical field decays into particles. So you just start with a classical field, which is large, for instance. You don't put any particle distribution in the propagators initially, and you let the system evolve. And what we expect is that after some time, the propagator will contain a particle distribution. And then the third extension we have in the back of our mind, but which probably is not feasible right now, is to extend that to young males. So here's the problem. Well, one will have to clarify how gauge invariance or residual gauge invariance works in this framework. But there will be also considerable computational issues because, well, a gauge field is like a scalar field with decorations. It carries a Lorentz index and a color index. And this means that the memory necessary will be far greater than what we needed for a scalar field. So that's why probably it's not feasible in the short future. Okay, thank you very much.
Thank you very much. That was very. So I'm actually amazed how much information you get out for on isotropization. I mean, this looked like a numerically very heavy task, right? And so can you give me an idea of how much computing time you went into those?
Well, okay, I can tell you. So first of all, I can tell you what is the kind of hardware we use. When we realize that what's going to kill us is the bandwidths, the memory bandwidths, and the speed at which you can move data around, we realize that it's not the kind of computation you can do on a cluster, because the interconnections between the nodes of a cluster are too slow. So it's something that you have to do on a single computer that has a sufficiently large amount of memory. So in the end, we're doing that on a computer that has of the order of 500 gigabytes of memory, or a little less. And it has also GPUs. So the computations which can be easily parallelized are processed on a GPU or on a few GPUs. And now regarding the amount of time it takes, I will say a run with the parameters I described will take 2 to 3 days on such a computer with 4 GPUs. And of course, we wasted a considerable amount of computing time in testing all these and playing with the parameters. So now that we have that under control, we can more directly do runs for physics. So it's not it's not a computation you can do on a laptop on your desk, but it's not some computation that will take several months also to complete. It's intermediate between the two. And of course, you can make it significantly faster by reducing a little bit the size of the grids and so on.
I think you guys have good questions. I have more, but I don't want to.
I have two. Again, so yeah, one is on this slide. So when you talk about maybe applying this to young nodes, so one of the big things here is the memory storage that you have to access and write a lot of memory very quickly.
Yeah, so let me go back here. Basically, so most of the storage is for storing the past history of the propagators. This is what takes the largest by far amount of memory. And all these propagators are accessed once per time step. So they are not written once per time step, but they are read once per time step. And then as you move by one time step, you discard the oldest propagators and you replace them by the slice of the newest propagators that you've calculated in the last time step. To avoid moving a lot of data around, what we did in the end is to have separate arrays for each. Where was it? No, it's here. So we have one separate array for corresponding to each dot on this grid. And instead of moving the data, we move the pointers to these arrays, which is super fast. But of course you need to read. You need the time to read all these propagators at every time step. The reason why this is necessary is that they enter in these equations. So you see that to compute these integrals, you will access all the propagators of the past time slices of the system, at least once per time step. So you need to be able to calculate them. The other part of the calculation is to compute the self-energies, but this is in fact rather short compared to computing these integrals.
If you were to try and move through the other models,
Can you speak louder? I don't hear you well.
from the side of the room, but yeah. So if you were to try and move into Young-Mills theory with this,
Yes.
the computational bottleneck would be in the same place, or would there be some kind of other?
Yeah, no, I think roughly the difficulties will be the same. The memory needs will scale by the number of Lorentz indices times the number of color indices. So if you were really doing Young-Mills with SU3, you will have 8 color indices and 4 Lorentz indices. So the memory you need will scale by a large factor. On a more fundamental level, there are probably still a few sticky issues regarding how one deals with gauge invariance. Because as you know, the propagators are not gauge invariant objects. So it means that to make sense of these equations, you will have to fix a gauge in a certain way to make the propagators unique. But then, of course, what you want in the end is to extract gauge invariant physical information about the system. So you will have to think harder about how to extract gauge invariant properties of the system from non-gauge invariant propagators.
Right. I have one more question.
Can I just follow up on that? Would you have any issues with like non-perturbative stuff creeping into this formalism if you try to do Yang-Mills or not?
Can you repeat the question, please?
All right, I said if you were doing Yang-Mills, would you have to worry at all about any non-perturbative objects creeping into this formalism, or is that avoided?
No, you will have to, in the sense that this formalism is not a magic box that will solve everything. In particular, if you, if your problem has physically relevant scales which are too soft, you will have the problem that the strong coupling constant becomes large and therefore it's non-perturbative in the soft sector. So this will be unavoidable. So here, probably it will not be too much of a problem if we choose, let's see, it's here. Yeah, here. If you choose a typical momentum in the initial condition to be large enough to be in a region of momentum where you trust perturbation theory for Yang-Mills. So if you have a Q which is a few GeVs, for instance, then you start to be in a region where alpha S is not so large and not to the point of making everything totally non-perturbative.
Okay, thank you.
It's the only moment. This Q is the only dimensionful scale in the setup. So you just have to choose it large enough. Now, whether the typical scale, which is realized in a heavy ion collision at the LHC, is large enough for this to be perturbative is another question. But this being a theoretical work, you're a priori free to choose Q as you like.
Okay, I have one question, but it may be a silly one or an obvious answer. So when you looked at the two particle irreducible the action itself, you performed well, you didn't. You have the expansion of that phi term for the. Why did you choose to truncate it where you did? Was that sort of?
Oh, okay. Yes, this I can explain. So, of course, including more terms will make everything just harder. What's believed is that this is the smallest set of terms that will give you scattering. So in fact, you can see that a little bit here. You see, when you take the functional derivative of phi respect to a g, it means that you cut one propagator open in these graphs. So if you do this for this graph here, you get a tadpole. Let's not discuss the graph with the background field because we set it to 0. And if you cut one line open to this graph here, you get a two-loop self-energy. And this two-loop self-energy is precisely the one that gives you two-body scatterings when you derive the Boltzmann equation. So in fact, truncating at this level is the how to say, it's a minimal set of graphs to be on par with what's included in the Boltzmann equation. Except that here in this framework, these graphs are treated without the approximations that give you the Boltzmann equation. I can tell you of another approximation which has been used in this context, but not with expanding coordinates like here, is to assume that you have not one scalar field but n scalar fields. So you take an ON model, so n scalar fields with an ON symmetry, and you take the large n limit, and in the large n limit, in fact, you can compute exactly the leading behavior of this phi in the limit where n goes to infinity. And then you in a sense you're not doing any approximation. You can solve exactly in full the large n limit of this theory, but it's numerically it's a considerably larger amount of work than what we did here with a single scalar field, and the
You're referring to Jürgen and Stromberg.
yeah, exactly. Yeah, so they did that in for systems which are confined in a finite volume, like here, but they have studied that.
All right, so they have put it in the box. This is exactly what I wanted to ask, right? How does it compare to what they did? So they had a finite box, something I didn't remember.
I'm only aware of two other works where people used the 2pi formalism for systems which are expanding. One is a work by Yoshihata and a student, I think he is called Nishiyama. They tried to do this, but this was like 10 years ago, and the resources they had at the time were, I think, insufficient to treat this properly. And then there is another work by Anders Strandberg, where he uses, but for cosmology, for the cosmological expansion. So he was studying inflation typically. So it was not the same type of expansion here. Here I have a longitudinal expansion in one direction. He had a three-dimensional isotropic expansion. But he also implemented the 2pi formalism for treating this problem.
Also at large in C or with another?
No, I think it was with just one scalar field,
Okay.
with typically within flattened field.
Okay. All right. Yep. I remember. That's been a while ago that I looked at this. So this is a little. Okay. So, I mean, the next questions are really. So what I find really intriguing is this, that looking at it like this gives you a notion of grab the particles out of the propagator, right? I mean, in terms of this of these occupation numbers.
Yeah.
Classical particle limits in other forms are really a tricky thing, right? I've not seen many alternative approaches to actually try and get that something like a classical electron out of QED or something like this. Do you know of any work in that direction?
No, I'm not so familiar with that. One thing I wanted to add is that here we could avoid totally speaking about particles if we were calculating the stress energy tensor. So this will be another way to characterize the anisotropy of the system that doesn't need that the system even is made of particles. The reason we tried, but we found that this was more sensitive to the residual dependence on the UV, because the stress energy tensor is a dimension 4 operator, and it's a lot trickier to renormalize. The fact that we have an incomplete renormalization at this point was causing rather large problems or rather large cutoff dependencies in the in the stress energy tensor. Otherwise, the stress energy tensor has a definition in terms of the fields and propagators that doesn't require you to talk about particles at any point. It's just measuring how the energy is distributed in the system. It doesn't care about.
And therefore, it would be one of the quantities that you would want to look at if you were, say, trying a gauge theory, right? Because
yes, exactly. It's
need
gauge invariant, unlike gluon distribution, which probably will cause serious problems when you try to
But
discuss.
nevertheless, right? If you have physical particles in your theory, I don't know of many approaches that would get at the particles, right? Without doing the Boltzmann kind of limit, which is a little much for my taste in this.
Yeah, no, this is
You would
true.
like to separate
But it's not totally. I mean, when we extract an occupation number, where is it? So it's here, for instance. You can see it here. So it's essentially what we do is that we assume that the propagator has approximately this form, and the formula I showed you essentially projects out this factor, which is made of the Hankel functions, to give you the prefactor, which is 1/2 plus the occupation number. So of course you can always apply this formula with the square root to the propagator. but the interpretation of the result as being the occupation number is only true if the propagator has this form. So in a sense, we cannot truly be sure that, how to say, the quasi-particle description is a good way of describing our system. It's just that if we apply this formula, it gives some number out, which we interpret in this way. But the big caveat is that the interpretation is robust only if the system or if a quasi-particle interpretation makes sense for this system.
Yep. Very good, very important. Do we have more questions? Well, then thank you. Thanks a lot. And
Thank you very much.
yeah. Why don't you stop recording? Yeah.